Welcome. Today we'll present about nitriding damage mechanisms as part of high-temperature corrosion greater than 400 degrees Fahrenheit or 204 degrees Celsius. Description of nitriding damage mechanisms based on API 571, a hard, brittle surface layer will develop on some alloys due to exposure to high-temperature process streams containing high levels of nitrogen compounds such ammonia or cyanides, particularly under reducing conditions. Here's a detailed description of nitriding damage. Introduction: Nitriding is a surface hardening process used to improve the wear resistance, fatigue strength, and corrosion resistance of ferrous metals, particularly steels and alloys. It involves diffusing nitrogen into the surface layer at elevated temperatures to form nitrides, creating a hard, wear-resistant surface. However, despite its benefits, nitriding can sometimes lead to damage if not properly controlled or if adverse conditions occur. Understanding nitriding damage is essential to prevent component failure and ensure optimal performance. Here's a detailed description of nitriding damage. Number 1 is, nature of nitriding process. Process parameters, typically conducted at temperatures between 500 degrees Celsius and 550 degrees Celsius or 932 degrees Fahrenheit and 1022 degrees Fahrenheit. Material reactions: nitrogen reacts with alloying elements such as chromium, aluminum, molybdenum, and vanadium to form nitrides. Surface characteristics: results in a hard, dense, and often brittle nitride layer on the surface while maintaining a tough core. Number 2 is, types of nitriding damage, includes, number A, cracking and spalling, described as formation of cracks within the nitride layer or at the interface with the substrate, which may spall or flake off, cause of cracking and spalling, includes, excessive residual stresses from nitrogen diffusion, rapid temperature changes causing thermal shock, inadequate control of process parameters. Brittle nitride layer due to high nitrogen content. Types of nitriding damage. Number B, blistering, described as formation of blisters or bubbles on the surface, often accompanied by flaking, cause of blistering, includes, trapped gases or impurities beneath the nitride layer, excessive nitrogen concentration leading to internal stresses, surface contamination or oxide layers interfering with uniform diffusion. Types of nitriding damage. Number C, porosity and pitting, described as development of pores or pits within the nitride layer, cause of porosity and pitting, includes, improper cleaning or contamination before nitriding, excessive diffusion leading to microvoids, hydrogen entrapment during processing. Types of nitriding damage. Number D, decarburization and loss of toughness, described as reduction of carbon content near the surface, weakening the material, cause of decarburization and loss of toughness, includes, high-temperature nitriding causing decarburization, overexposure, or prolonged nitriding cycles. Types of nitriding damage. Number E, distortion and dimensional changes, described as warping or dimensional inaccuracies due to differential expansion or contraction, cause of distortion and dimensional changes, includes, uneven heating or cooling, high residual stresses from nitriding. Number 3 of detailed description of nitriding damage is mechanisms leading to nitriding damage, includes, residual stress accumulation, the nitrogen diffuses into the surface, creating tensile residual stresses that can exceed the material's strength, thermal stresses, rapid heating or cooling induces thermal stresses, causing cracking, chemical incompatibility, inappropriate alloy composition or impurities can lead to uneven nitriding or phase formation, process control failures. Deviations in temperature, time, or atmosphere can produce non-uniform layers and damage. Description of nitriding damage. Number 4 is, common manifestations and symptoms, cracks visible on the surface or within the nitride layer, flaking or spalling of the nitride surface during operation, surface blisters or bubbles observed visually, increase in surface roughness or pitting, dimensional inaccuracies or warping. Nitriding damage manifests mainly as cracking, blistering, porosity, and surface spalling caused by residual stresses, thermal shocks, or improper process control. Proper material selection, precise process control, and thorough inspection are essential to prevent and detect nitriding-related failures. Nitriding damage affected materials based on API 571, Number A, carbon steels, low alloy steels, 300 series SS and 400 series SS. Number B, nickel-base alloys are more resistant. Here's a detailed explanation of materials affected by nitriding damage. Nitriding is primarily applied to ferrous alloys, especially steels and cast irons, to enhance surface hardness, wear resistance, and fatigue life. However, not all materials respond equally well to nitriding, and improper application can lead to damage. Understanding which materials are affected, and how, is crucial for selecting appropriate materials and processing parameters. Here's a detailed explanation of the materials affected by nitriding damage. Number 1 is, primary materials susceptible to nitriding damage, includes, number A, steels, carbon steels and alloy steels. Commonly nitride materials, includes, low to medium carbon steels, such as 1018, 1045, alloy steels, such as 4140, 4340, 9310, and other steels containing alloying elements such as Cr, Mo, V, Ni, hardenable steels, those designed for heat treatment, which often respond well to nitriding. Material characteristics, includes, contain sufficient carbon up to 0.1% to 0.5% required to form hard nitrides, alloying elements like chromium, vanadium, molybdenum, and aluminum improve nitriding response. Damage susceptibility, includes, cracking due to residual stresses if process parameters are not optimized, decarburization leading to surface softening, formation of brittle nitrides if overexposed. The next primary material susceptible to nitriding damage is cast irons. Types of cast iron, includes, gray cast iron, and ductile or nodular cast iron. Their response to nitriding can be nitride but are more prone to cracking due to their inherent brittleness. Damage includes surface cracking, spalling, or distortion. Another primary material susceptible to nitriding damage is stainless steels. Common grades includes 304, 316 or austenitic stainless steels. Some martensitic stainless steels such as 410, 420. Considerations: nitriding of stainless steels is more complex due to their corrosion resistance mechanisms. Damage can occur if nitriding conditions cause phase transformations such as formation of chromium nitrides that deplete chromium from the matrix, leading to sensitization and corrosion susceptibility. Number 2 of the materials affected by nitriding damage is materials less suitable or sensitive to nitriding damage. Number A, high carbon steels with excessive carbon. Excess carbon can lead to embrittlement or distortion during nitriding. Overly high carbon content increases risk of cracking. Number B, nonmetallic or poorly nitridable materials. Examples: aluminum alloys, titanium, copper and its alloys, non-ferrous metals. Nonmetallic or poorly nitridable materials do not form nitrides easily and can be damaged if subjected to high-temperature nitriding atmospheres intended for steels. Number C, certain cast alloys. Some cast materials with high porosity or impurities are more prone to blistering, porosity, or cracking during nitriding. Number 3 of the materials affected by nitriding damage is material microstructure and composition factors influencing damage. Number A, alloying elements. Elements like chromium, molybdenum, vanadium, aluminum, includes, facilitate nitride formation, can cause brittle nitride phases if overgrown or improperly controlled, lead to residual stresses due to phase transformations. Number B, carbon content, affects the formation of carbides and nitrides. High carbon can cause decarburization or carbide/nitride segregation leading to embrittlement. Number C, initial microstructure, includes, ferritic, martensitic, or bainitic steels respond differently. Martensitic steels tend to develop high residual stresses and cracks if nitriding is too aggressive. Ferritic steels can nitridize more uniformly but are still susceptible to cracking if process parameters are not optimized. Number 4 of the materials affected by nitriding damage is material damage mechanisms related to composition, includes, residual stresses. Alloys with certain compositions can develop high internal stresses during nitriding, leading to cracking, phase transformation. Certain compositions may undergo unwanted phase changes such as formation of brittle nitrides or carbides, causing embrittlement. Decarburization, materials with high carbon content can lose carbon from the surface under nitriding conditions, weakening the surface layer. Number 5 of the materials affected by nitriding damage is special considerations for non-standard materials, includes, composite materials. Nitriding can cause damage due to differential thermal expansion or phase incompatibilities. Coated materials. Protective coatings may be damaged or delaminate during nitriding. Summary table of the materials affected by nitriding damage. If material type is low to medium carbon steels, then the common issues during nitriding will be cracking, decarburization, distortion, and the susceptibility to damage will be high if process not controlled. If material type is alloy steels, then the common issues during nitriding will be residual stress buildup, brittle phases, and the susceptibility to damage will be medium to high depending on alloy and process. If material type is cast irons, then the common issues during nitriding will be cracking, spalling, distortion, and the susceptibility to damage will be high due to brittleness. If material type is stainless steels, then the common issues during nitriding will be phase changes, sensitization, cracking, and the susceptibility to damage will be medium, sensitive to heat treatment conditions. If material type is high carbon steels, then the common issues during nitriding will be embrittlement, cracking, and the susceptibility to damage will be high if overexposed. If material type is non-ferrous metals, then the common issues during nitriding will be no nitriding response, damage unlikely, and the susceptibility to damage will be not applicable. The susceptibility of materials to nitriding damage depends heavily on their composition, microstructure, and the nitriding process parameters. Proper material selection, process optimization, and pre- and post-treatment procedures are vital to mitigate damage and ensure expected material performance. Nitriding damage critical factors based on API 571. Number A, nitriding is a diffusion-controlled process dependent on temperature, time, partial pressure of nitrogen and metal composition. Number B, temperatures must be high enough to allow for the thermal breakdown or dissociation of nitrogen from ammonia or other compounds and for diffusion of nitrogen into the metal. Number C, nitriding begins above 600 degrees Fahrenheit or 316 degrees Celsius and becomes severe above 900 degrees Fahrenheit or 482 degrees Celsius. Number D, high gas phase nitrogen activity, high partial pressures of nitrogen, promotes nitriding. Number E, corrosion resistance may be adversely affected by nitriding. Number F, alloys containing 30% to 80% nickel are more resistant. Number G, a loss of high temperature creep strength, ambient temperature mechanical properties, specifically toughness/ductility, weldability and corrosion resistance may result. Here's a comprehensive, detailed explanation of the critical factors of nitriding damage. Introduction. Nitriding is a thermochemical surface treatment designed to enhance surface hardness and wear resistance. While beneficial, nitriding can sometimes lead to damage such as cracking, spalling, blistering, or distortion. These adverse outcomes are often the result of key factors that influence the process's success or failure. Understanding these critical factors allows engineers and technicians to optimize nitriding conditions, select appropriate materials, and implement proper pre- and post-treatment procedures to minimize damage. Number 1 of the critical factors of nitriding damage is process temperature. The impact is the nitriding temperature significantly influences nitrogen diffusion, phase formation, and residual stress development. Details: high temperatures, greater than 550 degrees Celsius increase diffusion rates but also promote excessive residual stresses, phase transformations, and decarburization. Low temperatures, less than 500 degrees Celsius reduce risks of distortion and cracking but may lead to insufficient surface hardening. Critical point: maintaining an optimal temperature, typically 500 to 550 degrees Celsius, balances diffusion depth with minimal residual stress buildup. Number 2 of the critical factors of nitriding damage is nitriding duration. The impact is, the length of the process influences the nitride layer's thickness and the accumulation of residual stresses. Details: overlong nitriding causes excessive nitrogen diffusion, leading to high internal stresses, brittleness, and potential cracking. Insufficient nitriding results in inadequate surface hardening and vulnerability to wear. Critical point: precise control of process duration ensures a balanced nitride layer with minimal damage risk. Number 3 of the critical factors of nitriding damage is atmosphere composition. The impact is, the gases used, such as ammonia, endothermic gases, or plasma, determine nitrogen availability and surface reactions. Details: pure nitrogen or ammonia provide controlled nitrogen sources but can lead to uneven diffusion if impurities or contaminants are present. Contaminants: presence of oxygen, moisture, or other impurities can cause oxidation, blistering, or porosity. Critical point: maintaining a clean, controlled atmosphere prevents surface oxidation and ensures uniform nitriding. Number 4 of critical factors of nitriding damage is temperature uniformity. Impact of temperature uniformity is uneven heating causes thermal gradients that induce thermal stresses. The details of temperature uniformity includes hot spots or cold zones, lead to differential expansion or contraction, resulting in cracking or distortion. Critical point: uniform temperature distribution within the furnace and on the component surface is essential to prevent localized stresses. Number 5 of the critical factors of nitriding damage is material composition and microstructure. The impact is, the alloy's chemical makeup and initial microstructure influence its response to nitriding. Details: alloying elements. Elements like Cr, V, Mo, Al enhance nitriding but can also promote brittle phase formation if not controlled. Carbon content. Excessive carbon can lead to decarburization or carbide precipitation, causing embrittlement. Microstructure: martensitic, ferritic, or bainitic structures respond differently. Martensitic steels are more prone to cracking under residual stresses. Critical point: selecting suitable alloys and microstructures minimizes damage potential. Number 6 of the critical factors of nitriding damage is residual stresses. The impact is, internal stresses developed during nitriding can exceed the material's strength, causing cracking or spalling. Details: sources, rapid nitrogen diffusion, phase transformations, thermal gradients. Mitigation: post-nitriding stress relief treatments, such as tempering or annealing, are often necessary. Critical point: managing residual stress levels is crucial to prevent crack initiation. Number 7 of the critical factors of nitriding damage is surface preparation. The impact is, surface cleanliness and roughness influence nitriding uniformity and defect formation. Details: contaminants, oil, dirt, oxides, or scale can cause blistering, porosity, or uneven diffusion. Surface finish: rough surfaces may trap gases or impurities, leading to blistering or pitting. Critical point: proper cleaning, degreasing, and surface finish improve process outcomes. Number 8 of the critical factors of nitriding damage is cooling rate and thermal shock. The impact is rapid cooling can induce thermal stresses, leading to cracking. Details: rapid cooling causes differential contraction, especially in thick or complex parts. Gradual cooling helps to relax residual stresses and prevent damage. Critical point: controlled, gradual cooling reduces thermal shock risks. Number 9 of the critical factors of nitriding damage is component design and geometry. The impact is, sharp corners, thin sections, or complex geometries concentrate stresses. Details: stress concentrators, sharp edges or abrupt cross-sectional changes increase risk of cracking. Design considerations: incorporate fillets, uniform thickness, and stress relief features. Critical point: proper component design minimizes stress concentrations during nitriding. Number 10 of the critical factors of nitriding damage is post-treatment processes. The impact is, post-nitriding heat treatments can relieve residual stresses and reduce damage. Details: stress relief annealing reduces internal stresses that could cause cracking. Renitriding, sometimes necessary if initial nitriding causes microstructural issues. Critical point: appropriate post-treatment ensures the component's integrity and performance. Summary table of critical factors of nitriding damage. If the critical factors is process temperature, then the effect on damage risk will be high temperatures increase residual stresses. Control measures to be taken should maintain optimal temperature 500 degrees Celsius to 550 degrees Celsius. If the critical factors is nitriding duration, then the effect on damage risk will be excessive time causes brittleness. Control measures to be taken should precise timing control. If the critical factors is atmosphere composition, then the effect on damage risk will be impurities cause blistering. Control measures to be taken should use clean, controlled atmospheres. If the critical factors is temperature uniformity, then the effect on damage risk will be uneven heating causes stresses. Control measures to be taken should ensure uniform furnace heating. If the critical factors is material microstructure, then the effect on damage risk will be inappropriate microstructure leads to cracking. Control measures to be taken should select suitable alloys and microstructures. If the critical factors is residual stresses, then the effect on damage risk will be excessive stresses cause cracks. Control measures to be taken should post-treatment stress relief. If the critical factors is surface preparation, then the effect on damage risk will be contaminants-induced defects. Control measures to be taken should clean thoroughly before nitriding. If the critical factors is cooling rate, then the effect on damage risk will be rapid cooling causes thermal shock. Control measures to be taken should cool gradually and uniformly. If the critical factors is component design, then the effect on damage risk will be sharp corners increase stress. Control measures to be taken should design with stress relief features. If the critical factors is post-treatment processes, then the effect on damage risk will be insufficient stress relief. Control measures to be taken should implement proper post-heat treatments. Mitigating nitriding damage requires a holistic approach, carefully managing all these critical factors. Proper process control, material selection, component design, and post-treatment are essential for achieving the desired surface properties while avoiding damage. Nitriding damage affected units or equipment based on API 571. Nitriding can occur at any location where appropriate environment and temperature conditions are met, but it is considered to be fairly rare. Nitriding has been observed in steam methane reformers, steam gas cracking, olefin plants, and ammonia synthesis plants. Here's a detailed explanation of the affected units or equipment of nitriding damage. Introduction. Nitriding is a high-temperature surface treatment process that involves specialized equipment such as furnaces, gas generators, and auxiliary systems. Damage during nitriding not only affects the workpieces but can also significantly impact the equipment used, leading to operational downtime, increased maintenance costs, and safety hazards. Understanding which units or equipment are susceptible to damage during nitriding helps in planning, maintenance, and process control. Here's a detailed explanation of the affected units or equipment of nitriding damage. Number 1 is nitriding furnace or heat treatment chamber. The key components affected includes heating elements and thermocouples, furnace refractory materials, furnace walls and linings, gas delivery and exhaust systems. Potential damage and causes. Overheating or uneven temperature distribution can cause cracks or deformation in refractory bricks. And thermocouple failure due to thermal shock or corrosion or oxidation from reactive gases, ammonia, nitrogen, can degrade furnace linings. Contamination or buildup of deposits from process gases can impair heat transfer and cause blockages. The impact of nitriding furnace or heat treatment chamber is furnace damage leads to operational downtime, costly repairs, and the need for replacement of critical components. Number 2, gas supply and control systems. The key components affected are gas regulators, valves, burners, and flow controllers. Potential damage and causes includes corrosion or erosion from reactive gases like ammonia, blockages or leaks caused by deposits or improper maintenance, pressure surges or fluctuations damaging control equipment. The impact of gas supply and control systems is disruption of the nitriding atmosphere, leading to inconsistent or defective treatments. Number 3 of the affected units or equipment of nitriding damage is vacuum or gas exhaust systems. The key components affected includes exhaust fans, ducts, filters, and scrubbers. Potential damage and causes, corrosion or buildup inside ducts from ammonia decomposition or nitrogen reactions, fan failure due to corrosion or mechanical wear, filter clogging from deposits, reducing airflow. The impact of vacuum or gas exhaust systems is poor exhaust management can cause safety hazards, environmental issues, or process failures. Number 4 of the affected units or equipment of nitriding damage is auxiliary equipment. Examples: temperature controllers, sensors, and data acquisition systems, sample holders and fixtures, loading and unloading mechanisms. Auxiliary equipment potential damage and causes, sensor drift or failure from high temperatures or reactive gases, mechanical wear or deformation of fixtures under thermal stress, contamination or corrosion affecting equipment longevity. Number 5 of the affected units or equipment of nitriding damage is post-treatment equipment, if applicable. For examples, cooling chambers, stress relief ovens, or tempering furnaces. Potential damage and causes of post-treatment equipment includes thermal fatigue or distortion due to rapid cooling, equipment corrosion from residual gases or moisture. Number 6 of the affected units or equipment of nitriding damage is handling and transportation equipment. For examples, carts, racks, or fixtures used to load or unload parts. Potential damage and causes includes corrosion or degradation from exposure to nitriding atmospheres, mechanical wear from repeated handling under high temperatures. Number 7 of the affected units or equipment of nitriding damage is environmental control systems. For examples, ventilation, fume extraction, and safety systems. Potential damage and causes, fume buildup due to leaks or system failures, corrosion of ventilation ducts from reactive gases. Summary table of affected units or equipment in nitriding. For equipment or unit is nitriding furnace or chamber, the possible damage will be cracks, deformation, refractory degradation. They will cause as high temps, thermal shocks, corrosion, and the consequences would be downtime, costly repairs. For equipment or unit is gas supply and control systems, the possible damage will be leaks, corrosion, regulator failure. They will cause as reactive gases, contamination, and the consequences would be process inconsistency, safety hazards. For equipment or unit is exhaust and ventilation systems, the possible damage will be corrosion, clogging, fan failure. They will cause as gas reactions, deposits, and the consequences would be environmental and safety issues. For equipment or unit is auxiliary equipment, sensors, fixtures. The possible damage will be sensor failure, deformation. They will cause as thermal stress, corrosion, and the consequences would be inaccurate control, equipment failure. For equipment or unit is post-treatment equipment, the possible damage will be thermal fatigue, corrosion. They will cause as rapid cooling, residual gases, and the consequences would be reduced lifespan, safety risks. For equipment or unit is handling and transport, the possible damage will be corrosion, mechanical wear. They will cause as exposure to reactive atmospheres, and the consequences would be equipment failure, safety risks. For equipment or unit is environmental control systems, the possible damage will be leaks, corrosion, fume buildup. They will cause as system failure, improper maintenance, and the consequences would be safety hazards, environmental pollution. Damage to equipment during nitriding can have serious operational, safety, and financial implications. Proper maintenance, material selection, and process control are vital to mitigate equipment damage. Regular inspections, corrosion protection, and adherence to safety standards help ensure equipment longevity and process reliability. Appearance or morphology of nitriding damage based on API 571. Number A, nitriding is usually confined to the surface of most components and will have a dull, dark gray appearance. However, during initial stages of nitriding, damage can only be seen with metallography as shown in Figure 4-130, Figure 4-131 and Figure 4-132. See Figure 4-130, a nitride 5Cr 0.5 mo thermal well from an ammonia synthesis plant with surface cracking. See Figure 4-131, a photomicrograph of a cross-section through the tube showing the interface between the shallow nitride layer on the surface, gray, and the unaffected base metal, white. Cracks initiate from the OD surface at the top. Mag. 50x. See Figure 4-132, a higher magnification photomicrograph showing the diamond-shaped hardness indentations in the hard nitride layer, 540 Bhn, versus the softer base metal, 210 Bhn. Mag. 150x. Number B, in a more advanced stage, the material will exhibit very high surface hardness. In most cases, a slightly harder surface layer of a vessel or component will not affect the mechanical integrity of the equipment. However, the concern is for the potential development of cracks in the nitride layer that could propagate into the base metal. Number C, nitriding of low alloy steels containing up to 12% chromium is accompanied by an increase in volume. The nitride layer tends to crack and flake. Number D, above 770 degrees Fahrenheit, or 410 degrees Celsius, preferential grain boundary nitriding may lead to microcracking and embrittlement. Number E, stainless steels tend to form thin, brittle layers that may crack and spall from thermal cycling or applied stress. Number F, nitrogen diffuses into the surface and forms needle-like particles of iron nitrides, Fe3N or Fe4N, that can only be confirmed by metallography. Here's a detailed explanation of the appearance or morphology of nitriding damage. Introduction. The visual and microstructural appearance of nitriding damage provides critical clues about the underlying causes and severity of the issues encountered during or after the nitriding process. Recognizing specific damage morphologies helps in diagnosing process faults, selecting appropriate mitigation strategies, and improving future treatments. Number 1 of the appearance or morphology of nitriding damage is cracking patterns. The appearance and microstructure includes transgranular cracks propagate through the grains, often appearing as fine, branching lines across the surface. Intergranular cracks follow grain boundaries, often appearing as networks of cracks along the interfaces. Crazing manifests as a network of fine, shallow cracks resembling a spider web. Cracking patterns causes and morphology includes result from residual stresses exceeding the material's fracture toughness, often initiated at surface defects, inclusions, or stress concentrators. Cracks may be visible as sharp lines or rough, jagged features on the surface. Number 2 of the appearance or morphology of nitriding damage is blistering and bloating. The appearance are rounded, blister-like protrusions on the surface. Blisters may vary in size from micrometers to millimeters. The surface around blisters may appear shiny or rough. Blistering and bloating morphology and microstructure, caused by gas entrapment beneath the surface, often nitrogen or reaction gases. Gas pockets form during nitriding, creating subsurface voids that exert pressure, causing blistering. Blisters can rupture, leaving pitted or rough areas. Blistering and bloating visual clues: smooth, dome-shaped elevations, possible peeling or flaking if blisters rupture. Number 3 of the appearance or morphology of nitriding damage is spalling and flaking. The appearance would be flakes or chips of material detaching from the surface, usually associated with severe cracking or blistering. Spalling and flaking morphology and microstructure: failure of the nitride layer or substrate due to high residual stresses or brittle phases. Spalled regions often show rough, uneven edges. Under microstructural examination, spalled areas reveal brittle fracture features. Spalling and flaking visual clues: rough, jagged edges where material has separated. Fracture surfaces may appear granular or fibrous, indicating brittle failure. Number 4 of the appearance or morphology of nitriding damage is porosity and pitting. The appearance would be small, round or irregular voids on or beneath the surface. Pits may be shallow or deep, with rough or smooth contours. Porosity and pitting morphology and microstructure: pores form from trapped gases or impurities. Excessive porosity weakens the surface and promotes crack initiation. Micrographs show voids within the nitride layer, sometimes extending into the substrate. Porosity and pitting visual clues: surface irregularities with a crater-like appearance, may be associated with blistering or flaking. Number 5 of the appearance or morphology of nitriding damage is decarburization and microstructural changes. The appearance would be surface may appear dull, softer, or with different coloration. Microstructural examination reveals changes such as carbide dissolution or formation of brittle phases. Morphology of decarburization and microstructural changes: loss of carbides leads to a loss of hardness and brittleness. Micrographs show a deoxidized or softened layer with altered grain structure. Decarburization and microstructural changes visual clues: changes in surface finish or color. Microstructural features such as enlarged grains or carbide depletion zones. Number 6 of the appearance or morphology of nitriding damage is distortion and warping. The appearance would be bending, twisting, or uneven warping of components. Surface or edges may appear uneven or deformed. Morphology and microstructure result from thermal stresses and residual stress buildup. Microstructural evidence includes microcracks or uneven phase distribution. Distortion and warping visual clues: deformed geometry, surface irregularities, cracks, or distortions. Number 7 of the appearance or morphology of nitriding damage is microcracks and fine fractures. The appearance would be very fine, hairline cracks visible under a microscope. Usually not easily visible to the naked eye but can sometimes be seen as a network of faint lines. Morphology and microstructure of microcracks and fine fractures would be initiated by residual stresses, phase transformations, or thermal shocks. Microcracks often follow grain boundaries or are randomly distributed. Microcracks and fine fractures visual clues, detected via microscopic examination rather than macro inspection. Summary table of morphologies of nitriding damage. For damage type is cracking, the visual or morphological features will be fine or coarse cracks, sometimes branched, and the typical causes will be residual stresses, brittle phases. For damage type is blistering, the visual or morphological features will be dome-shaped protrusions, and the typical causes will be gas entrapment, surface oxidation. For damage type is spalling or flaking, the visual or morphological features will be chips or flakes detachment, and the typical causes will be high internal stresses, brittle layer formation. For damage type is porosity and pitting, the visual or morphological features will be pores or craters, and the typical causes will be gas entrapment, impurities. For damage type is decarburization, the visual or morphological features will be dull, soft surface, microstructural changes, and the typical causes will be excessive temperature, decarburizing atmosphere. For damage type is distortion, the visual or morphological features will be warped or bent parts, and the typical causes will be thermal stresses, uneven cooling. For damage type is microcracks, the visual or morphological features will be fine network of cracks, and the typical causes will be residual stresses, phase transformation stresses. The appearance and morphology of nitriding damage provide essential diagnostic clues. Recognizing these features allows for understanding the underlying causes, whether process-related, material-related, or equipment-related, and implementing appropriate corrective measures. Nitriding damage prevention and mitigation based on API 571, changing to more resistant alloys with 30% to 80% nickel is usually required. It is usually not practical to modify the process conditions to reduce the nitrogen partial pressure or to lower temperatures. Here's a comprehensive, detailed explanation of prevention and mitigation strategies for nitriding damage. Introduction. Nitriding is a valuable surface hardening process, but it can be prone to various forms of damage such as cracking, blistering, porosity, and distortion. Preventing these issues requires a combination of proper process control, material selection, equipment maintenance, and post-treatment procedures. Number 1 of prevention and mitigation strategies for nitriding damage is material selection and preparation. The key principles includes, use materials with suitable composition and microstructure for nitriding, ensure high purity and cleanliness to reduce inclusions and impurities, pre-treat materials to relieve residual stresses. Detailed actions in the material selection and preparation activities includes, choose appropriate steels or alloys, steels with controlled nitrogen affinity and stable microstructures, such as low-carbon steels. Nitriding steels like 17CrNMO6 are less prone to damage. Avoid materials with high residual stresses. Stress relieved or normalized prior to nitriding minimizes internal stresses that can cause cracking. Clean surfaces thoroughly, remove grease, oxide layers, and scale via grit. Blasting, degreasing, or acid pickling to prevent contamination that can lead to porosity or uneven nitriding. Number 2 of prevention and mitigation strategies for nitriding damage is optimized process parameters. The key principles includes, control temperature, gas composition, and time precisely, avoid excessive nitriding temperatures that can cause decarburization or brittleness, use suitable gas atmospheres and pressure to prevent excessive internal gas entrapment. Detailed actions in optimized process parameters activities includes, temperature control, keep nitriding temperatures within the recommended range, typically 500 to 550 degrees Celsius. Avoid rapid temperature changes to prevent thermal shock. The next is to optimize gas composition, use a controlled ammonia or nitrogen atmosphere to minimize gas decomposition and internal gas entrapment. Incorporate proper gas flow rates to ensure uniform atmosphere and prevent localized overheating. The next is to optimize process duration, limit nitriding time to achieve the desired case depth without overexposure, which can cause excessive internal stresses. Number 3 of prevention and mitigation strategies for nitriding damage is pre- and post-treatment mechanical processes. The key principles includes reduce residual stresses before nitriding, relieve stresses after nitriding if necessary. Detailed actions in pre-treatment, stress relieving or normalization reduces internal stresses, surface finishing, such as polishing, shot peening, can improve surface integrity and residual stress distribution. Detailed actions in post-treatment, low-temperature tempering or stress relief annealing can reduce residual stresses induced during nitriding. Controlled cooling minimizes thermal shocks and distortion. Number 4 of prevention and mitigation strategies for nitriding damage is equipment maintenance and process control. The key principles includes maintain equipment to ensure uniform temperature and gas flow, regularly inspect and calibrate process controls. Detailed actions in furnace maintenance, check refractory lining integrity to prevent uneven heating, maintain uniform heating elements. Detailed actions in gas system checks, ensure gas flow and pressure are stable, replace filters and scrubbers regularly to prevent contamination. Detailed actions in monitoring and control, use accurate thermocouples and sensors, implement real-time process monitoring to detect deviations early. Number 5 of prevention and mitigation strategies for nitriding damage is controlling cooling and heating rates. The key principles is to avoid rapid temperature changes to prevent thermal stresses. Detailed actions in controlling cooling and heating rates includes, the first is gradual heating and cooling, ramp temperatures slowly during heating and cooling phases, use controlled cooling environments to prevent thermal shocks. The second is cooling media, use inert or controlled atmospheres during cooling to prevent oxidation or decarburization. Number 6 of prevention and mitigation strategies for nitriding damage is use of protective coatings and surface treatments. The key principles includes, protect surfaces from oxidation and contamination, enhance surface integrity and reduce stress concentrations. Detailed actions in use of protective coatings and surface treatments includes, applying coatings, such as boron nitride or ceramic coatings, to prevent oxidation and improve process uniformity. Surface peening, shot peening or laser peening introduces compressive residual stresses, reducing crack initiation. Number 7 of prevention and mitigation strategies for nitriding damage is process inspection and quality control. The key principles includes, detect early signs of damage or process deviations, use non-destructive testing or NDT to assess surface and microstructural integrity. Detailed actions in process inspection and quality control includes, visual inspection, look for blistering, cracking, or surface irregularities, microstructural analysis, use metallography to detect porosity, decarburization, or brittle phases, hardness testing, ensure case hardness meets specifications without excessive brittleness, residual stress measurement, use X-ray diffraction or other methods to assess internal stresses. Number 8 of prevention and mitigation strategies for nitriding damage is post-nitriding treatments and repairs. The key principles includes, correct or relieve pre-existing damage, enhance surface properties and longevity. Detailed actions in post-nitriding treatments and repairs includes, stress relief annealing, to reduce residual stresses, remachining or grinding, remove damaged or cracked surface layers, renitriding, reapply nitriding process after repairs if necessary. Summary table of prevention and mitigation strategies for nitriding damage. For strategy and use is material selection and preparation. The key actions to be taken is, use suitable alloys, clean surfaces. The expected outcome for this strategy is to reduce internal stresses, fewer defects. For strategy and use is process parameter optimization. The key actions to be taken is, precise temperature, gas control. The expected outcome for this strategy is to uniform case, minimized internal gas entrapment. For strategy and use is process parameter optimization. The key actions to be taken is, precise temperature, gas control. The expected outcome for this strategy is to uniform case, minimized internal gas entrapment. For strategy and use is equipment maintenance. The key actions to be taken is, regular inspection and calibration. the expected outcome for this strategy is to consistent process conditions. For strategy in use is controlled heating or cooling, the key actions to be taken is, gradual temperature changes, the expected outcome for this strategy is to minimize thermal stresses. For strategy in use is protective coatings, the key actions to be taken is, surface protection during nitriding, the expected outcome for this strategy is to reduced oxidation, improved surface quality. For strategy in use is inspection and quality control, the key actions to be taken is, NDT, microstructural analysis, the expected outcome for this strategy is to early detection of defects. For strategy in use is post-treatment repairs, the key actions to be taken is, stress relief, remachining, the expected outcome for this strategy is to damage mitigation, extended component life. Preventing nitriding damage involves a comprehensive approach that integrates material science, process engineering, equipment maintenance, and quality control. Proper planning and adherence to optimized process parameters significantly reduce the risk of damage, ensuring durable, high-quality nitride components. Nitriding damage inspection and monitoring based on API 571, number A change in surface color to a dull gray may indicate nitriding. Number B, materials exposed to nitriding conditions should be inspected thoroughly because good appearance may mask damage. Number C, hardness testing of the affected surfaces, 400 to 500 bhn or higher, can help indicate nitriding. Number D, nitride layers are magnetic. Therefore, 300 series SS should be checked for magnetism as an initial screening. Number E, metallography is generally required to confirm nitriding. Number F, EC testing may be used in some cases to detect nitriding. Number G, in the advanced stages of nitriding, where cracking may have initiated, appropriate inspection techniques include PT, RT, and UT. Here's a detailed overview of inspection and monitoring methods used to detect nitriding damage. Introduction: detecting nitriding damage early is critical to prevent component failure, ensure quality, and optimize process parameters. A variety of inspection and monitoring techniques are employed, ranging from visual assessments to advanced non-destructive testing, NDT, methods, to evaluate surface integrity, microstructure, and internal stresses. Number 1 of inspection and monitoring methods for nitriding damage is visual inspection. The purpose of this visual inspection is rapid, initial assessment for surface defects such as blistering, cracking, spalling, or discoloration. Visual inspection methods: use of magnifying lenses or microscopes for detailed surface examination, inspection under good lighting conditions, sometimes with UV or infrared light for specific defects. Visual inspection methods used to identification of surface anomalies like blistered or bubbled areas, cracks, transverse, longitudinal, or branching, flakes or spalled regions, discoloration indicating decarburization or oxidation. Visual inspection limitations: cannot detect subsurface or microstructural damage, subjective, depends on inspector experience. Number 2 of inspection and monitoring methods for nitriding damage is microscopic and microstructural examination. Number A of its is optical microscopy. The purpose of optical microscopy is to observe surface microcracks, porosity, or phase changes. Method of optical microscopy is preparing metallographic samples, polishing and etching. Optical microscopy is to detect microcracks, grain boundary issues, or brittle phases. Number B of microscopic and microstructural examination is scanning electron microscopy, or SEM. Its purpose is high-resolution imaging of surface and subsurface features, used to identify microcracks, porosity, or inclusions. Additional method is energy dispersive X-ray spectroscopy, or EDS, for compositional analysis. Number C of microscopic and microstructural examination is microhardness testing. It is purpose to assess hardness profiles across the nitride layer. Method: indentations under controlled loads, detection, variations indicating decarburization, brittle phases, or uneven case depths. Number 3 of inspection and monitoring methods for nitriding damage is non-destructive testing or NDT techniques. Number of NDT techniques is ultrasonic testing or UT. Principle of UT is high-frequency sound waves detect internal discontinuities, application of UT technique is to detect internal porosity, cracks, or delaminations, measure layer thickness and uniformity. Methodology of UT, use of immersion or contact probes, echo analysis to identify reflections from flaws. The advantages of UT is deep internal inspection, suitable for thick components, and the limitations of UT is less effective for very small or surface-breaking cracks. The NDT technique is X-ray radiography or computed tomography or CT. Its principle is, X-rays penetrate the material, flaws appear as radiolucent areas. Application of this radiography or CT technique are to detect internal porosity, cracks, and voids. 3D imaging with CT provides detailed internal microstructure. The advantages is precise localization and characterization of internal damage, and the limitations is costly, requires specialized equipment. The NDT technique is magnetic particle inspection or MPI. The principle of MPI is to detect surface and near-surface cracks in ferromagnetic materials. Methodology of MPI includes magnetize the component, apply ferrous magnetic particles, surface defects cause magnetic flux leakage attracting particles. Advantages of MPI is effective for surface cracks, especially in steels. Limitations of MPI is only suitable for ferromagnetic materials. The next NDT technique is dye penetrant testing or DPT. Principle of DPT is surface breaking flaws are revealed by dye seepage. Method of DPT includes apply penetrant liquid, remove excess, apply developer to draw out penetrant from cracks. Advantages of DPT is surface cracks, blisters, and porosity. Limitations of DPT is cannot detect subsurface flaws. Number 4 of inspection and monitoring methods for nitriding damage is residual stress measurement. Number A, X-ray diffraction or XRD. XRD purpose to measure residual stresses induced during nitriding. XRD method used to analyzing diffraction peak shifts. XRD apply to high residual stresses correlate with crack initiation risk. Then residual stress measurement. Number B, neutron diffraction. It is used to non-destructive residual stress measurement in thicker components. Number 5 of inspection and monitoring methods for nitriding damage is case depth and hardness profiling. It is purpose to verify the uniformity and adequacy of the nitride case. This method's used to microhardness profiling, measure hardness at incremental depths, nidal or acid etching, reveal case depth by microstructural contrast, measuring equipment, portable hardness testers or microhardness testers. Number 6 of inspection and monitoring methods for nitriding damage is monitoring during nitriding process. Number A, process sensors, temperature sensors, thermocouples, to ensure uniform heating, gas flow meters and analyzers to monitor atmosphere composition, residual gas analyzers, RGAs, for detecting unwanted gases, and number B, real-time data analysis, process parameters logged continuously, early detection of anomalies such as temperature spikes or gas deviations. Number 7 of inspection and monitoring methods for nitriding damage is post-process inspection and quality control, routine inspections after nitriding based on criticality, statistical process control, SPC to monitor process stability over time, documentation, maintaining detailed records of inspections for traceability and process improvement. Summary table of inspection and monitoring techniques for nitriding damage. If method in use is visual inspection, it is purpose for surface defects, its capabilities is to detect cracks, blistering, discoloration, and the limitations is, this method cannot detect subsurface flaws. If method in use is metallography, it is purpose for microstructure analysis, its capabilities is to detect microcracks, phases, porosity, and the limitations is, destructive sample preparation. If method in use is scanning electron microscopy or SEM and microhardness, it is purpose for microstructure and hardness profile, its capabilities is to detect microcracks, phase changes, and the limitations is, costly, microsampling. If method in use is ultrasonic testing, it is purpose for internal flaws, its capabilities is to detect cracks, porosity, and the limitations is, less sensitive to small cracks. If method in use is X-ray radiography or computed tomography or CT, it is purpose for internal defects, its capabilities is to detect voids, cracks, and the limitations is, expensive, complex setup. If method in use is magnetic particle, it is purpose for surface cracks, its capabilities is to detect surface flaws, and the limitations is, only ferromagnetic materials. If method in use is dye penetrant, it is purpose for surface cracks, its capabilities is to detect surface flaws, and the limitations is, no subsurface detection. If method in use is X-ray diffraction XRD and neutron diffraction, it is purpose for residual stresses, its capabilities is to detect stress profiles, and the limitations is, equipment intensive. If method in use is process sensors, it is purpose for process monitoring, its capabilities is to detect temperature, atmosphere, and the limitations is, not flaw detection. A comprehensive inspection and monitoring regime combining visual, microstructural, NDT, and process parameter controls is essential for early detection of nitriding damage. Regular inspection helps maintain high quality, optimize process parameters, and prevent costly failures. Thank you.